So our next speaker is Robert Rooy. He started at IBM NL in 1994, joined IBM UK in 1995, and did his first 1024-node HPC installation in the late 2000s. From 2001, he worked for IBM US in pre-sales as HPC Advanced Technical Support, before returning it to Europe in 2006 to become an HPC architect. With IBM's x86 divestiture, moved to Lenovo in 2015. He's been with Lustre for almost 2 years as a senior HPC system engineer for data services, which encompasses, amongst other things, the DDN Lustre solution currently deployed at Meluxina.
Good morning. So first a little bit about Lustre. For those that are not aware, Lustre is a relative newcomer in the sector. It was set up by the Luxembourg state to procure, host, and run basically a European class or supercomputer. This was all started, or the installation was started early 2001. Basically, the system is in operation. We are a member of EuroHPC. On 35% of the system is available through EuroHPC. As I said, the mission is basically that we have to accelerate economic and social progress through supercomputing. We, of course, have a lot of Luxembourg customers. We also, as I said before, are available via EuroHPC, who have a 35% share of the system for European research. So this presentation is about the snapshots, and of course the snapshots need to take place on storage. So Meluxina has 4 Lustre file systems, of which 3 are listed here. So we have a scratch file system. You can see on the left-hand side, 12 building blocks, 0.6 petabyte usable. This is all DDN storage, all of them. We have a project home file system, 10 building blocks, 12 petabyte usable. This is the file system on which we did snapshot testing, and for which the snapshot functionality was requested, basically. And then there is a bunch of backup systems and tape libraries and these kind of things as part of the storage solution. So, Lustre snapshots. Clint Eastwood, yes. Luckily not in this order, but we did have some rough spots at the beginning. So the snapshot requirements were pretty basic. To be honest, they were also coming from a GPFS perspective. We were originally expecting to have a GPFS installation. This turned out to be a Lustre proposal instead, that one. So from a snapshot perspective, we were of course looking for creation and deletion. Multiple snapshots needed to be taken to be able to hold a week's worth of data. These snapshots could not have a real noticeable user impact when creating snapshots. And they should have a minimal performance impact when the snapshots are in place on the system. In addition, from a future wish list, basically, we were also looking for an easy way to provide users access to snapshot data, and to allow partial file system snapshots, because at the moment we can only take snapshots of the entire file system. We cannot do a partial snapshots. So the snapshot functionality was requested, or demanded, I could say, by the tender. It was a hard requirement. This was originally committed by the vendor for availability at the tail end of 2020. There were various delays pushing this out into 21. At that point in time, some of the functionality was missing that we were looking for, which pushed things out further. And then when we got to the actual implementation of it, we ran into multiple operational issues with regards to availability of the file system. I will not go into all of the nitty-gritty details here, but it was a long, drawn-out process. Eventually, the system was accepted in July 2020. After co-design and testing, we did deep technical work on partnership with DDN here was essential. That's what the next slide will be about. So after these initial issues, to their credit, DDN prepared an action on the test plan, quite a comprehensive plan. They set up actually two systems in the US. One that was near identical to our system in regards to the MDT, OST counts, and OST size as our Meluxina system. This was for their in-lab development and testing. They also provided us access to this test system via VPN. They provided weekly calls with DDN developers, on WAM Cloud developers, on DDN management. During these testings, multiple issues were found. I think that they created about a dozen internal tickets or something like that for new issues discovered during this time period. The majority of them were found by DDN in their own testing, which is good. We found another couple of issues with our testing on their system. These issues were resolved, at least the critical issues were all resolved. There were still some performance issues which were pushed out to future releases. But all in all, the product was greatly enhanced. Some examples of additional enhancements, basically, the snapshot destroy is now by default asynchronous, so that not the entire user file system freezes when you do a snapshot create. Snapshot destroy is asynchronous, so it will basically immediately return and it will be done in the background at lower priority. And there is new snapshot stat functionality to actually see what's going on in the background, something that was completely invisible before this. Not all of that functionality is actually in the current Exascaler releases. Some of them is basically being pushed out to future releases, LDISC FS updates, on these kind of things for the future. From a testing and benchmark methodology, we had some core needs, of course. We needed to ensure the platform stability, something that we had experienced problems with prior. We couldn't have any crashes during the creation, deletion, or mounting of the file systems. We also needed to make sure, of course, the usability of the file system. We couldn't allow any real interruptions during user access, so home directories, that's part of our problem. The home directories are on this file system, so any freezes of the file system or unavailability of the file system will immediately impact users. No application impact, crashes or corruption, and ensure the performance, so minimal differences in performance with or without a snapshot in place on the system. So from a testing of benchmarks, we did two things. From our perspective, from a Lux Provide perspective, we did synthetic testing using MD-test, and we did application testing using GROMACS, OpenFOAM, and PyTorch. The application testing really wasn't too focused on performance, it was more focused on stability. So for instance, taking pausing the application and restoring the application afterwards, basically, these kind of functions were done with snapshots in between to make sure that there was no data corruption in place when we restart the application from a checkpoint. This all worked actually fine. We didn't actually experience any problems with that. So even doing a checkpoint restore from a snapshot worked fine. From the MD test, there I fortunately did save some of my data. Some data of the application test unfortunately was not retrievable anymore at this point in time when I was asked to prepare a presentation. So what we did is I did a scripted run of MD test. For this we had 7 nodes available. These were the Fujitsu nodes that were available on the DDN system. With Mellanox interconnect, 80 cores per node. So we did so I created a loop, did a snapshot create, ran MD test. After the create at 0, 10, 30, 60, and 120 minute intervals after it, to see the performance impact over time of a snapshot create. Would loop over that 5 times, so basically create 5 snapshots. After that, start destroying snapshots and creating new snapshots, as you would probably do in real life, because you would not endlessly be creating snapshots, obviously. So the older snapshot would be deleted, and then we again run the MD test, and that was done in 2 loops. And at the end, we purged the remaining snapshots of the system. So this is to verify the stability and usability and the performance of the snapshot functionality. So based on this, this is some aggregated data. This is not from a single run, actually. This is from a whole bunch of runs where I've taken the median of. So as you can see, the standard deviation, it's quite reasonable. We're seeing in stat operations, we were seeing some degradation in performance. You have to take into account that this actually was running on the 2.14 version of Lustre because of the ARM support, whereby on Meluxina we're actually running on the 2.12 version still. But on the test system from DDN, we could only use 2.14 for the clients. But on the server side, it was 2.12. So the standard deviation or the difference with and without snapshots is really not that great. We're seeing a little bit of a difference in tree removals, which are IOPS, not kilo IOPS. For file and directory, everything is in kilo IOPS here. And once again, this is on the DDN system, actually the smaller one of the DDN system. This is not actually the one that was more or less equivalent to the Meluxina system, because this was done at the tail end and they were reprovisioning the other system at this point in time, these runs. So some interesting tidbits, the performance recovery. So what happens when you take a snapshot, basically? How long does it take for the system to more or less recover from those snapshots? And as you can see, there's a little bit after, so on the left-hand side, you have no snapshots at all. Then the next one is immediately after the snapshot create, we run an MD test. And then we do another one 10 minutes after. As you can see, there's a bit of a dip that goes down, and then the system starts to more or less recover. Some of the operations are more stable than other. As you can see here, the colors may not be too clear, but basically the file stat, as mentioned before, sees the biggest impact in the directory on the file. On file create and also has a little bit of a dip. The tree operations are all over the place, it seems, in all cases. It sees quite an impact after the create, so at 0 minutes, basically, we see quite a dip down from just over 35 to under 20 operations per second. On the tree removal, well, that's is a very difficult one, basically. It seems to be all over the place, even when you even it out over multiple runs, basically. So this is the performance numbers, basically. And that's really the end of what I have to present on this presentation. So that's, I don't know if you want to do questions or you want to present some of the technical part of your side of it.
Okay. Question? Maybe I missed the information. How many snapshots do you take per day, week? What is the frequency?
In actual operation now, after the deployment of the functionality.
Yeah.
So we're not actually taking regular snapshots at the moment. We're taking occasional snapshots, simply because of some of the prior history. We're still a little bit hesitant of doing continuous snapshots at this point in time, basically. We are looking to start using it in full production. On that point in time, we're probably looking to create 5 snapshots in a rolling fashion, basically. So we would always have 5 snapshots on the system, once every day, basically. On that way, the users could request files to be restored. And this is also mirrored in our requirements our wish list for the future, that we would like to have a user access to these snapshots. Because right now, the way, I don't know if you're familiar with how snapshots work in Lustre, but the snapshots create and then exporting the snapshots to the clients and then mounting it on the client is quite a process. Basically, it's not that easy to automate, especially with the amount of failure situations that can occur with this. That at the moment we would probably do it on demand. So the user would tell us, I would like to restore some files, basically, and we would then do it that way. And then over time we would look to automate this with scripting, basically, to make this available, unless, of course, some additional enhancements are made available by DDN to us, which make it easier, like is available on DPFS with the dot directories.
Okay.
So let me just ask to get it straight. So how you restore files is that you mount the snapshot on a temporary mount point and then you copy the files between the mount points?
Correct. That's indeed how it works. Yes. So on the we first need to run snapshot mount on the storage itself. That creates the export. And then on the client, similar to how you mount any Lustre file system, but instead of you use the snapshot ID basically as the name of the file system, and that's how you mount it on the client on a temporary mount point. And then the user can then restore his files because the access rights are the same. The user can then restore basically the files that he needs to restore from the snapshot. That's correct.
Are the snapshots read-only, I guess? Or
Sorry?
the snapshots are read-only?
The snapshots are read-only, yes. The snapshots cannot be written to.
I have a last question. Have you evaluated the impact on the OST part?
The impact on the backend, on the OSTs?
Yeah.
Well, the impact on the OSTs doesn't seem to be very high. It seems to be mainly metadata related. We did not really do many tests on the OST performance, but we didn't really notice too much of an impact on it. Okay. Like I said, it seemed to be mainly metadata operations. That's why we were looking at IOR performance.
Exactly. Okay, thank you.
Do I have to go to a different presentation? Hi, so I'll be talking about the sort of the more technical aspects of how snapshots was implemented. So we did look at a number of different options for how we might implement snapshots in Lustre. And I mean, DDN, mostly uses LDiskFS for their deployments. I mean, we did look at ZFS, and so, ZFS has integrated snapshots, that's great. ZFS has other features. As Torben had mentioned, one of the issues with ZFS is the performance, right? And in particular, we had worked at Intel for quite a number of years to improve ZFS performance, metadata, and things like that, but it's still lagging. And in particular for high IOPS usage with Flash, you really notice a significant difference, and so we didn't wanted to change over to ZFS. There was also a separate project, Fujitsu, that had DL Snap, and so, you know, that had a benefit that it was in use on the K computer. One of the negative issues there, several negative issues. One is that the code was very old. It was originally developed for Lustre 1.8 and, you know, hadn't seen very much update, and they were not very interested in doing any updates, even though the code was eventually made available to the community. But the other technical issue is that the DL Snap requires that every single file that's being snapshotted is processed. And so if you're doing a snapshot on a file system that has, you know, 1 billion files, it's more like a small directory kind of functionality rather than a whole file system functionality. And so we didn't think that that was going to be very practical. And so there was another set of patches that were submitted into upstream ext4 from a company named Cetera. And those provided whole file system snapshots. There was already E2FS progs and E2FS CK support for it. There had been some work done to reserve, you know, metadata fields in the upstream, you know, kernel for those snapshots. And because it's LDiskFS, you know, ext4 based, you know, this provides a way for existing DDN systems to use the snapshot functionality. But, you know, again, while the patches were against newer versions of ext4, they still did need some updates. And the other area that ended up needing quite a bit of work was handling very large file systems. I mean, originally the Cetera patches were only for file systems up to 16 terabytes. And so that's not very practical for Lustre. But it looked like the best solution at the time. And so we based the snapshot work on that. And essentially, the way that the snapshots are implemented is that inside LDiskFS, essentially a snapshot is a virtual image of the file system. And I mean, we wanted snapshots at the LDiskFS level partly to match how ZFS was implemented, so we can use the same commands, we can you know, have consistency between the different backends, but the snapshots, each target takes a snapshot of the local disk file system. So for each OST and each MDT, we get an independent snapshot, and you know, they can be either, you know, taken all at one time with a barrier, which essentially blocks all client I/O to the file system and all metadata operations. And while that's, you know, seems appealing, you know, one of the issues is that it has a performance impact to the running application. And it turns out that that's, you know, while it seems like, oh, I want an atomic snapshot, that's great. It turns out that it's actually not, you know, as great as you might think, because even if you're taking an instantaneous snapshot, you still don't know the state of the applications at that time, right? So if applications are writing to the file system, you know, they might be right in the middle of a syscall and have lots of dirty cache. And even if we flush the cache, they might be, you know, writing half of a file. So you can't really expect that snapshots being taken, you know, while applications are running are going to get you consistent data. And so Lustre itself, because it's an aggregation of independent file systems, we can already handle the fact that there might be some inconsistencies between the MDTs and the OSTs and things like that. So the snapshots are not taken essentially atomically, and we just run them asynchronously in the background. So at the file system level, essentially each snapshot is a full virtual image of the entire file system. And so when the snapshot is created, you get an empty file system. It has a copy of the super block and things like that, and we export the snapshot images as loopback files to user space, and then we can mount them using regular, Lustre tools to mount the file system image. This works for both Lustre mounting and LDiskFS mounting, and we can do things, like running E2FSCK against the snapshot images to make sure that the snapshot itself was taken correctly. One thing we did have to do is implement a file format that supports larger than 16 terabyte files. And because of the nature of how snapshots are created as random, IOP block IO, because you don't know what blocks are being modified, we ended up going with an indirect file format rather than extents. And so that's actually a 5-level indirect tree. We call it 5ind. But that format is only used for snapshot files. And so even though it's not supported in upstream ext4, when you delete the snapshots, those files go away. And so we can always, pick a different format in the future if we need to. And the code itself ended up being about 10,000 lines in LDiskFS for the snapshots and about 5,000 lines for the 5ind large file format. But a lot of that is boilerplate. It just means add in, instead of indirect, double indirect, triple indirect, quad indirect, 5 indirect. It's a lot of boilerplate code. So even though it's a lot of lines, it's not as much complexity as you think. And when you're modifying, after you've created a snapshot, when you're modifying the files, you have this initially sparse file, and if you make a modification, say you're modifying an inode, it will take a copy of that block and write it into the snapshot file, because in LDiskFS, the metadata locations are fixed, and so we have to write a copy into the virtual, location of the snapshot file at the right offset. For data blocks, we instead of copy on write, we have move on write. So you don't actually make a copy of the data blocks, which is the biggest volume of data. You move the pointers for those data blocks to the virtual inode inside the snapshot file, and then you overwrite a new set of blocks in the regular file system. And that's fine because all file blocks in a file system, when they're being modified, they're being wholly overwritten anyways, so it avoids an extra data copy and performance impact. Because even with if you're writing 1 byte of data to a file, the Lustre client is going to do a 4K read, modify, write. And so we'll always get at least block size IOs into the snapshot. And, we have to exclude blocks, that are part of the snapshots themselves, so we don't recurse and make the transactions big. On the read side, if there's holes in a snapshot, it will, read through to the next older snapshot or to the main file system, so that we don't have to make copies of all the data and metadata in the snapshot files. So, this was already covered a lot. We did do testing, up file systems up to 500 terabytes. And, one of the things that we noticed is the snapshot creation for very large file systems can, take some time, but we did improve the performance of that significantly over time. Initially we had been doing the development, on smaller file systems and with NVMe, and that worked fine, but the very large, hundreds of terabytes OSTs did require some extra work to optimize the snapshots. And I think this is the last slide here. So we did originally develop and test it on EL 7.9, which is the current server kernel for Exascaler. Most of the changes are in LDiskFS. We did have some user tool work. And what else? FSCK, you can run FSCK on the snapshots. We can't actually fix a snapshot if it were appear to be corrupt, but you can delete them. It's just like deleting a regular file. So it's actually not very complicated to delete snapshots. And E2FSCK minus X will delete all of the snapshots and then, clear up the block references and things like that. So it's relatively low risk from that side if there's a problem with the snapshots. And we're just in the process of porting this to EL 8.6 kernels. And I think that's it.
Thank you. Any questions?
Does the snapshotting affect quota after copy on write? effects?
Well, we did have issues with the quotas because it was counting that as extra space against the users. But because it's a copy, if a user deletes their file, for instance, but there's a copy in the snapshot, they're not charged for the copy that's in the snapshot, right? As you'd expect. Yeah, it's only the data in the main file system that's counted.
I understand this is a exascaler addition. Do you have any plan to release those changes open source?
We're currently, just updating it. It's against an older kernel, and I mean, RHEL EL 7.9 is not even supported in, 2.15. So it does need some updates. There's some management questions there too, but eventually, yes, that's one of our goals, just to reduce the maintenance and things.
Thanks.
I understand that taking a snapshot during the workload does not guarantee any coherency from an application point of view.
Yeah.
But I think the barrier feature tried to have something coherent between MDT and OSTs, especially on the file system metadata. So I feel like it's still useful to have that, like to guarantee in-flight operation from the MDT to the OSTs, these kind of things to be coherent.
Yes and no. I mean, Lustre itself can handle a lot of the inconsistency. I mean, the most error that you would see, it's not like, let's say, GPFS, where the blocks have to be consistent across all of the storage, right? With Lustre, because each file system is independent, I mean, the snapshots are still, atomic on the per file system level. And so the most that you would see is in some cases, let's say if you, we're deleting a file and the OST snapshot finished before the MDT snapshot, you might get like enoent when you're trying to access a file, right? But it's not going to cause problems for Lustre. Right, so but those files, I mean, if they're right in the middle of being deleted when you create the snapshot, it's kind of, it's a race condition on whether you take the snapshot a millisecond before you delete it or a millisecond after, right?
But with barrier, you avoid this kind of case.
Yes, but even taking the barrier, I mean, you're quiescing, if it's a large cluster, you're quiescing the I/O, across 1,000 nodes, that might take minutes to flush all of the data out, right? And so it can be disruptive to the application.
Okay, thank you.
I have just a complementary question about this. Are you going to support the LFCK on the snapshot to gain about coherency?
No. Because you can't modify, the snapshots are read-only, so you couldn't fix it anyway.
Okay. Any other question? Okay. Myself again. I have seen that you rely on a kernel loopback driver for the copy of the image.
Yeah.
You are supporting the EL7 kernel, and you know that the loopback driver has some significant stat performance, in fact. Have you seen this? Because if you go through the loopback driver, you will have some poor performance.
Yeah, I mean, we did look at patching the loopback driver in EL7. I mean, it's better in newer kernels, but it's also different structure. I mean, we don't actually change the loopback driver. We're just using it to access the virtual, file inside the snapshot. And actually, one thing that I didn't put in my presentation was about the question about how easy or hard it is to access a snapshot. That's one of the areas of development, so that you know, you can auto mount the snapshots on the clients and things like that. And I mean, we'll actually try to make it more transparent so that you don't see them as, you know, separate file systems on the client, but that's a lot more work, you know, getting the base functionality, and newer kernels have better support for loop and things.
Okay.
All right.
Thank you.